Okay, so we're going to look at using the geometric series formula essentially to create power series that represent functions. In our case, we're going to be looking primarily at rational functions, since that is the form of our geometric series summation. But in future lessons, like when we work on Taylor series, we will be able to create power series for things that are not rational functions. We're going to look at two special cases in this discussion where the derivatives of the functions are power series. And so therefore we can create power series from those. Now, the general idea is that if you have a geometric series, so you have some constant a and then r to the n, that there is a finite sum in the cases where r meets the conditions for convergence, in which we can write the value of that sum. And what we're going to essentially do is we're going to do this process in reverse. So we are going to have a function which is expressed something like this. A can be itself a function of x in this particular circumstance. R does not have to be x specifically. It can be something else. It can have constants. It can be other powers of x, things like that. But we're going to use this template in the reverse direction to take our polynomial function and turn it into a power series. Now, the power series that we're going to get in many cases is not going to be convergent on the entire interval in which the original function was convergent. We're going to talk a little bit about how we can shift the center if we need to be at doing approximations at a slightly different point along that domain. But there are going to be many advantages in order to having a power series representing a function. Our power series are in some ways basically an infinite polynomial, and those are very easy to take. Polynomials are very easy to take derivatives of and things like that. So it has many advantages. So we're going to look at a couple of examples for applying this technique. So I have this function 1 over 1 minus 4x squared, and I want to write this as a power series. So what I need to identify for my power series formula, which we had up here or up here, is I need to find the value of a and I need to find the value of r. So I'm going to analyze the form of my polynomial, and I'm going to identify r as 4x squared, and in this case, a is just whatever in the numerator, which here is 1. Now, it's very important to keep in mind this constant in the denominator has to be a 1, and the sign should be negative. If it's positive, then we would split it up into a minus and then a negative, and then we would have one negative for the formula, and one negative would go into the power series. But in this case, it's already just one negative, and so our r is this positive value of 4x squared. And so we're going to plug in our a, where the a is in the formula, and the 4x squared in where the r was in our formula. And then we do some simplification. 4 to the n can come out, and then x squared to the n, raising powers to powers, you multiply the exponent. So you get x to the 2n. Now, to determine where the power series converges, then you would need to take your r value. Again, power series, this is a geometric series fundamentally. Your r value would have to be less than 1, and this would occur. You take the square root of both sides of this, and you get 2x, the absolute value of 2x is less than 1, and then you go from there. Now you would have to check then the endpoints, as we saw with other power series, to determine whether one of the endpoints should be included. But this is basically a pure geometric series, and so neither endpoint ends up converging. Now, in the case of this example, we have to do a little bit of fixing here. One of the issues that we have in this scenario is that the constant in the denominator is not 1, and it is in the geometric series formula. So how do we fix that? Well, essentially, we're just going to divide every component of our expression by whatever this constant is. In this case, 6. So we're going to divide out the 6. And when we divide out the 6, we're going to take 3x over 6. That's going to give us 1/2 x. 6 over 6 gives us the 1. And then, as previously noted, the formula requires a minus sign. So we split this plus sign into a minus minus. One of the minuses is part of the formula, and the other minus is part of the r value. So here, a is 1/2 x, and r is negative 7 over 6x. And then we plug that into the formula. So here's our a value, and then here is our r value. And then we have to do a little bit of simplifying. How much simplifying you do is going to depend a little bit on various things. But one thing that is very important is that any expressions of x inside your problem need to be combined into a single expression. So this x and this x to the n get combined into x to the n plus 1. And that's going to be very important, again, because when you try to take the derivatives later on in other applications, you do not want to have to do a power rule. And you don't want to have to do integration by parts if you're integrating. So you need to combine these. What the rest of the constants do is a little less important because those are, of course, just constants. And of course, depending on what you need to do, if you're just asked to write the function as a power series, then you're done. If you need to find the interval of convergence, then you would have to go through the process that we went through in some other videos. Now, another thing that you might be asked to do for some of these problems is to perhaps change the center of where you are doing your expansion. Now, in a typical problem like this, where you have 1 over 1 minus x, the center of this problem is actually at 0. But if we don't want to center it at 0, then we can maybe do our approximation at another location. Maybe we want to shift it to 2. Now, to do that, we would have to essentially rewrite our expression so that we could get this written in those terms. Now, essentially, the way that you want to do this, the way that I think about it, is I would set, there's different ways to go about it, but if you have 1 minus x and you replace x with x minus 2, which is going to make it centered at 2 instead of 0, then the problem that you're going to have is that now that you've added that or subtracted that 2 from the expression, what does that do to the rest of the problem? So you have to make sure that your denominator does not change value. So if, in this case, because this is minus x and I replaced it with x minus 2, technically I'm adding x because this is minus a minus, so I'm adding a 2 to my denominator. If I add a 2 to my denominator, I have to then subtract it from someplace else. And so I'm going to subtract that 2 from the constant. And again, if you FOIL everything out, you should make sure you get back to 1 minus x. But we need it in this x minus 2 expression, so I'm just going to combine the 1 minus 2 and get negative 1. Now, again, I have to have a leading 1, as I saw before, so I put a minus sign through my denominator, and I move that minus sign to the top. And so now I have an expression that is ready for my formula. A is this negative 1. R, because this is a plus sign, is negative x minus 2. You could also put it in as 2 minus x. That's fine. Although when you do derivatives, you will then have to deal with that negative sign. So it may be easier to just put it in as a negative x minus 2 in parentheses. And pull out the negative 1 to the n. But either is technically fine. And so we would end up with this expression, or you could rewrite this if you left the negative sign here. You could rewrite this as -1 to the n plus 1, because you would get n negatives from this expression and then one more, and then x minus 2 to the n. And of course, from this point, you would have to find the interval of convergence. And when you do that, you can confirm that it is in fact centered at 2. Instead of being from -1 to 1, it's now from 1 to 3. So it's the same length of convergence, but now it's just the center is at another point. Now, there is one additional trick that we can talk about, and that is these two, there are two functions, arctangent and log, where if you take the derivative, you get a rational expression. So the derivative of log is 1 over x, and the derivative of arctangent is 1 over 1 plus x squared. Both of these are rational expressions, and that means we can use them with our power series formula to write a power series for them, but write a power series for their derivatives. Once we find the power series for their derivatives, we can then integrate that result, do the antiderivative, in order to obtain a power series for the original function. Now we're going to walk through one of these examples. For the log function, this is x is centered at 0, and it's not defined at 0. So you're going to have to do something like the example that we were just looking at, where you're shifting the center off of 0, maybe to 1 or something like that, which is typical, and then proceed from there. The arctan doesn't have that initial issue, so we can go ahead and we can find the power series for that much more easily without having to jiggle things. So here's our arctan example. Its derivative is 1 over 1 plus x squared. And so a would be 1, and r would be -x squared, because of the plus sign in the formula. We need it to be a negative. And when you take your -x squared to the n, that simplifies to -1 to the n. That's your alternating component, x to the 2n. Now that is the power series for the derivative. And so remember that the summation is just a sum of terms with different values of n plugged in. And so if I want to integrate that, I can simply pull the summation outside of my integral and then integrate my formula. The -1 to the n is still a constant, so it doesn't matter as far as x is concerned, since that's the variable we're integrating with. And then x to the 2n is just a power rule. And so I get x to the 2n plus 1 divided by 2n plus 1. And now this expression is going to be a power series that represents arctangent. And of course, different variations on arctangent will work basically the same way with slightly different numbers. So if we had arctan 2x, this would be 1 plus 4x squared. And then we would have, again, a similar but slightly different answer. Those are all of the basics for just the general geometric series formula. Now, this is not the place where we can stop. In fact, there are some additional tricks that we can do to find power series for even more complex rational expressions, and we're going to do that in another video.